Okay, so thank you for the opportunity to speak here. Everything I'll talk about is joint work with Nick Sheridan. Some of the later things are work in progress. So the broad aim of the talk is to give symplectic applications of homological mirror symmetry, which remain rather scarce. So let me introduce the player that I'll focus on for the first sort of 2/3 of the talk. So let's consider this family of quartic hypersurfaces of CP3 parameterized by a complex coordinate lambda. So there's a sort of action of the group Z mod 4 times Z mod 4 on all of these. So it's easiest maybe to see this as well, you think about Z mod 4 acting on all of the coordinates of projective space fiber-wise. That's a Z mod 4 to the 4th. The diagonal acts trivially. That gives you a sort of copy of Z mod 4 cubed. And we think about the kernel of the sum map going to Z mod 4. That gives us a Z mod 4 times Z mod 4, which acts on these hypersurfaces and moreover preserves their holomorphic two forms. So these are generically smooth quartic K3 surfaces. So the general fiber has 6 A3 singularities, and we'll resolve those. So we'll replace each of those singularities by a chain of 3 rational curves. And so the general fiber here, I mean, after dividing by pi. And when we resolved these, so since we were dividing by a finite group that preserved the holomorphic two form, we got a singular K3 surface. We resolve its singularities, and we get another K3 surface, which is known as the mirror quartic. So, let me call that X. It contains these 18 exceptional curves coming from the resolutions of these 6 A3 singularities. And there's a hyperplane class. And an instance of the Green-Plesser mirror story, as discussed by Nick, tells us something about the Fukaya category of this mirror quartic when equipped with appropriate toric Kähler forms. So if this is so X, this resolution can be seen as a hypersurface in an appropriate toric variety given by sort of resolving the quotient of P3 by this finite group. This is equivalent to the derived category of coherent sheaves on a mirror space which is a quartic K3 surface defined over the Novikov field lambda. So lambda is the same Novikov field that figured throughout Nick's talk. And here, as in Nick's talk, this occurs as, a quartic defined by a specific set, a specific sort of polynomial equation where the monomials arising are indexed by these sort of resolution curves and something that corresponds to the hyperplane, and the valuations of the coefficients of those monomials encode the cohomology class of this toric Kähler form. So let me just say defined by explicit monomial equation whose coefficients valuations, that's to say the sort of minimal non-zero Novikov power occurring in the coefficient of a particular monomial, is encoding some data about the cohomology class of this toric Kähler form, and these toric Kähler forms belong to some open cone in the 19-dimensional space spanned by these 18 resolution curves and the hyperplane. Could I do, sorry? Write much bigger. Yes.
And also the edges, the thing.
In my defense, I was on time. It's absurd. So it seems to be a day for talking about irrationality. So let omega be an irrational toric Kähler form in the sense that the coefficients of omega written in this sort of set of 19 divisors are linearly independent over Q. So then we have three statements about the symplectic topology of the K3 surface sort of X equipped with this particular irrational toric Kähler form. So did I get too close to the edge again? You can't see anyway. There's a gigantic brick in front of you. You're just showing off. So this first statement says that if we think about the sort of Torelli group of this symplectic manifold, so you could think either of the kernel of the action of the symplectic mapping class group on cohomology, or in fact even the kernel of the natural forgetful map from the symplectic to the smooth mapping class group, then that's infinitely generated. The second is kind of, not very important, but I find it cute, so I wrote it up. So if S is a Lagrangian sphere, well, it's a classical fact, I guess, imported to us in this subject by Kronheimer-Feyer-Seidel, that the square of a Dane twist in a Lagrangian sphere in a four-manifold is smoothly isotopic to the identity. In particular, its cube is itself. So a Dane twist always has a cube root in pi naught of diff, but this says that the Dane twist in a Lagrangian sphere in this particular K3 has no cube root in pi naught of simp. And the third statement is that if L is a Lagrangian torus with vanishing Maslov class, then L defines a non-zero and indeed primitive class in homology. And just as a remark, a statement sort of very close to, maybe equal to C, was proved but never written down using related but somewhat different techniques, again in using ideas of mirror symmetry by Paul in the case of the quartic K3. So what I'd like to do is say something about, how these results are proved. To the extent that I focus on something, I'll focus on C, because I think it's the thing that Nick has not talked about for those of you who are involved in his colloquium talks. And the proof will make essential use of mirror symmetry, so we'll attack these problems by problems on the derived category, and in particular, what we'll do is stand on the shoulders of Bridgeland.
Can you write larger on our shoulders?
Maybe. Okay, so I want to tell you a little bit about stability conditions, a theory that Tom Bridgeland's developed over a long period. I won't have time to say very much. So let X naught be a K3 surface over C. So there's a non-empty complex manifold which is really associated to the triangulated category, which is the bounded derived category of coherent sheaves on X naught, called the space of stability conditions. And a point of the space of stability conditions comprises sort of two pieces of data which satisfy some axioms that I won't talk about. There's a homomorphism from the sort of numerical Grothendieck group, the kernel of the quotient of K0 of the category by the kernel of the Euler form. So for us, this will look like the complexification of a lattice, which is given by H0 plus H4 plus the Picard lattice. So there's a complex valued homomorphism on this lattice, and there's a collection of subcategories of phi semi-stable objects, whatever that means. And these are bound together in various ways. They satisfy a number of axioms, but the only axiom for later purposes I want to sort of draw specific attention to is a kind of Harder-Nirasimhan axiom. So every object has a Harder-Nirasimhan filtration, which looks like the following. So E is some non-zero object in the category, and we get a collection of triangles that decompose E, sort of exact triangles in the category, such that these sort of pieces, the semi-stable factors AI, are in these categories of semi-stables and of decreasing phase. Okay, so a stability condition is, two pieces of data, a collection of subcategories, which in a suitable sense let you build all objects, and this kind of central charge. So it's highly non-obvious that any exist. But once you have one, Bridgeland's remarkable theorem is that you get a complex manifold of such, and because these are defined only using the category, the group of equivalences of the category sort of tautologically acts on this. And sort of geometric group theorists tell us that the best way to understand a group is to make it act on a space, and this gives us a space that this group of equivalences of a triangulated category can act on. So, using this, Bayer and Bridgeland prove a number of results, but I want to focus on two. And the results I want to discuss both impose a condition on the K3 surface that the Picard rank of the K3 surface is 1. So then the group of equivalences of this category, the bounded derived category of coherent sheaves, fits into an exact sequence as follows. Sorry, let me say. So in the middle we have, well, not quite the group of equivalences. I've chosen to state it for the group of Calabi-Yau equivalences. These are the autoequivalences of the category that preserve said duality isomorphisms. So these are And sort of Bayer and Bridgeland observed that it's equivalently the autoequivalences that act trivially on the second Hochschild homology of the category D of x0. So the group of equivalences of the category certainly acts on the group of automorphisms of the cohomology of the variety, and something special to K3 surfaces is that it acts by integral automorphisms. And then this is by definition the sort of kernel of this action on cohomology. Okay? So this is, we get sort of always, but they identify sort of this essentially mysterious piece with the fundamental group of an explicit period domain. This is the content of their, or maybe the orbifold fundamental group of an explicit period domain. And without saying what that is in detail, I just want to say what the sequence then looks like in the case of the mirror quartic, where we'll be able to see what the terms sort of mean. So a general quartic over the complex numbers has just the hyperplane from P3. That's its sort of only interesting line bundle. So it is indeed Picard rank 1. The square of the generator is 4. Then the Bayer-Bridgeland sequence becomes something extremely concrete. So in the middle, we're meant to have the fundamental group of some period domain. Well, at the beginning, I wrote down a one-parameter family of quartics indexed by a coordinate lambda. This is actually invariant under dividing lambda, multiplying lambda by a fourth root of unity. So you could think of that family of quartics really as parameterized by sort of lambda to the fourth, and it would have three special fibers. There's infinity, there's the fiber at 0, where replacing lambda by lambda to the fourth didn't do anything, and there's one additional singular fiber. I said this fiber generally had 6A3 singularities, but there's one additional singular fiber, where there's a nodal singularity even after resolving the 6A3s. So this is pi1 of an orbifold P1 parameterized by lambda in the previous explicit family. And this group Z mod 2 star Z mod 4 arises as the equivalences of the lattice given by combining H0 plus H4, a hyperbolic plane, with this Picard lattice, the rank 1 lattice. So I should maybe say that this is pi1 of the upper half plane minus an infinite but locally finite set of points. Okay. But so once you understand what this is and you understand what this is and you see that this is the sort of natural map, then it's not hard to see that the kernel is an infinite rank free group. Okay. And there's a second result that I want to quote from Bayer and Bridgeland. If E is semi-rigid, meaning that it has sort of two-dimensional x1, so sort of x1 parameterizes deformations, so if that was 0, you'd think of the object as being rigid. For duality reasons, this is always even rank, so this is kind of the next case along from the object being rigid. Then there exists a stability condition such that E is semi-stable. So let me make a couple of remarks on so, I identified this kind of Z star Z mod 4 as the fundamental group of a family in which the mirror quartic K3 that I first talked about would live as one fiber. So via symplectic monodromy, it's sort of easy to construct a sort of homomorphism from pi 1 of this period domain, this sort of Z star Z mod 4, to the symplectic mapping class group of my mirror quartic, which then acts by autoequivalences of the Fukaya category or the derived Fukaya category of the mirror quartic. And by contrast, it's very hard to build the map from this pi 1 to autoequivalences of the derived category of this generic, Picard generic quartic surface, which is what Bayer and Bridgeland do. But on the other hand, as far as I can tell, we have no techniques currently in symplectic topology to show that this map, which it's easy to build, is onto. And what the algebraic geometry buys us here is that this much harder map to construct, they do understand under this Picard rank 1 hypothesis, is actually onto. Or onto the Calabi-Yau equivalences. Oops. With that in mind, let me just note, however, that even if one set up a homological mirror symmetry statement which lets one identify these categories, the monodromy map and the Bayer-Bridgeland map are built in sufficiently different ways that it's not by any means obvious from the proof of mirror symmetry that this diagram commutes. The second remark I want to make is just to say sort of something about this second theorem of theirs to do with the fact that you can make semi-rigid objects semi-stable, because it's an argument in which you clearly see why they need to make this Picard rank 1 hypothesis. So well,
here you have Pilot period odd to the third, and up here it looks just for the upper left-hand corner, you have Pilot period pi 0 sim. How are these fitting?
sorry, which things related?
So on the current board,
Yep,
you have Pilot period odd to,
yep.
and then up here you have Pilot period pi 0 sim and then to the odd to.
Yeah, it's just,
Is this a sequence or is this a
no, it's just a composition. I mean, the pi naught of sim acts on the autoequivalences of the Fukaya category. So by monodromy, what I naturally land in is the symplectic mapping class group, which is somehow the thing from the point of view of symplectic topology we were a priori interested in before Fleur. And we can access those parts that survive into the autoequivalences of the Fukaya category, and currently we don't know how to say much beyond that for general manifolds. That's okay. So suppose I have some semi-rigid E, any stability condition sigma. I said that a stability condition has this kind of central charge part, this homomorphism from this sort of complexified n of x, that's actually C3 in our case when the Picard rank is 1 to C, but the sort of Z of sigma is always actually given by sort of the pairing of Z sigma of some object K is given by pairing some particular vector omega with the Chern character of K, or maybe more properly the Mukai vector of K, where this is the sort of Mukai pairing. And the conditions on this sort of period type point say that its real and imaginary parts span a positive definite two-plane in the real three-dimensional space, NXR. So that has sort of a one-dimensional orthogonal. Say that's spanned by some vector theta. And recall that one of the features of being a stability condition is that I have this kind of decomposition into semi-stables. So there are kind of outermost semi-stables there for any object, the ones of largest and smallest phase. So say in sigma, E has sort of semi-stable sort of extremal factors of phases phi plus and phi minus. And well, what Bayer and Bridgeland do is, you have a stability condition, you have this central charge, and they write down a differential equation, a flow on the space of these possible central charges. Which looks roughly like d omega dt is psi dot theta, where if I just draw a picture, so I have sort of an A plus, which is a maximal slope semi-stable factor, and an A minus, which is a minimal slope semi-stable factor. And I think about sort of trying to flow those together by a flow that moves this way. So if this orthogonal vector is psi, then perhaps up to a sign to make sure I push these together and not apart. Sort of infinitesimally, if I solve this differential equation, then I squeeze together the slopes of the sort of maximally separated stable or semi-stable factors of this object. So if I manage to flow for all time, eventually, you know, the semi-stable factors all have the same phase. That's just saying it's sort of semi-stable. It doesn't break up into things of different phase. But to choose this theta, I sort of needed this unique orthogonal direction, which was something about being Picard rank 1. So I think the geometry of that's quite intriguing, because if you've met the idea of stability conditions before, then they were motivated to a great extent by the idea that on the Fukaya category, you should get stability conditions from special Lagrangian submanifolds. So there was always an idea that given a Lagrangian, you should try and flow it to make it stable. But what the Bayer-Bridgeland theorem does is somehow flow the holomorphic volume form, leaving the Lagrangian submanifold alone. Okay, so there's something that I've elided so far, which is that, as Nick carefully explained, when one proves mirror symmetry, what one gets on the other side is a variety over the Novikov field, and at least at first sight, Bayer and Bridgeland's work is written for complex K3 surfaces, but sort of as is classical in the algebraic geometry literature, and we learned from Daniel Huybrechts largely. So it's a general fact that the generic quartic over lambda has Picard rank 1. And we have, in our HMS statement, a family of quartics over some affine space over lambda, parameterized by these explicit monomials arising from the exceptional resolution curves. And this affine space has a valuation map, which takes the valuations of the Novikov coefficients of the monomials. So inside this, there are loci of quartics of higher Picard rank, but these are well known to be algebraic subvarieties, and the image of an algebraic subvariety under the valuation always lies in some linear hyperplane. In fact, in Q-linear hyperplanes. But we're free to vary our original toric Kähler form in an open set in the Kähler cone. And I said that, Nick explained that the valuation coefficients of the particular monomial you write down exactly record the data of the cohomology class of the Kähler form. So in the HMS statement, we can ensure that x check d omega has Picard rank 1 by choosing omega to be irrational. So that explains the origin of this kind of irrationality hypothesis in the statement of the symplectic consequences. So at this stage, there's still a little bit more to say, although that's classical in the right communities, which wasn't us, but so now I take my irrational Kähler form, I obtain a Picard rank 1 mirror over lambda, but the K3 over lambda is defined over a much smaller field, over a finitely generated extension K naught of Q, and such fields and their algebraic closures embed into C. So this sort of general idea seems to be called the Lefschetz principle. And using this, you can sort of bootstrap back results that are known about K3 surfaces over C to K3 surfaces over the Novikov field in particular. So something that's contained in Daniel's beautiful book on K3 surfaces is that the autoequivalences of our K3 surface over the Novikov field sort of corresponds bijectively to the autoequivalences of a complex model obtained in this way. Okay. So I hope somehow the template for how the first set of theorems is proved is now sort of relatively clear. So I made sort of 3 symplectic statements. One of them was about this symplectic Torelli group. Well, here we see at least an infinite rank free group occurring as the autoequivalences of a derived category of some Picard rank 1 K3 that act trivially on cohomology. So by mirror symmetry, that tells us something about the autoequivalences of the Fukaya category of this irrational K3 surface that act trivially on cohomology. In fact, the fact that they're even smoothly trivial follows from older work of Seidel on squared Dane twists. The Dane twist in a Lagrangian sphere looks like the generator of this Z subgroup. It acts by an involution on cohomology, and it has no cube root in this group. Okay, so the sort of once you put yourself into a position where you can appeal to these results, then they're relatively straightforward. So the template is used by a Bridgeland, being careful. And let me just sort of try and illustrate one point that brings out the sense in which you have to be careful regarded to this statement about Lagrangian tori. So for instance, if L inside my irrational K3 is a Lagrangian torus with Maslov class 0, then it has a sort of mirror object E, which is some semi-rigid complex, defined over lambda. We can choose a field where both this K3 over lambda and this semi-rigid complex are both defined, so we can think we're working over C. Sort of semi-stability of E for some stability condition implies that the Chern character of E is non-zero, which sort of goes over to tell you that the homology class of L is non-zero. But in fact, the Chern character of E has sort of Mukai pairing plus or minus 1 with the Chern character of some spherical object. This is not so hard to check using classical results of Mukai. You use a Fourier Mukai transform to move E to the skyscraper sheaf at a point on some model of your K3 surface. So this looks very good for primitivity, but back in symplectic topology, we don't really have a good grasp of exactly what integral means. And in particular, it's not a priori obvious that the Chern character of a general spherical object of the derived category is an integral class. Okay, and if that was a general question about understanding integral structures in Floer theory, of course, we'd be stuck, hence the reading group on integral structures. But in this particular case, we understand enough about spherical objects and the lattice they span that we can sort of get around this by being careful. So, okay, so to end, I just want to talk for a few minutes about a completely different example related to a sort of different circle of ideas that ties into Daniel's talk from yesterday. I think it was yesterday. So let's recall from Daniel's talk that if Y is a cubic fourfold, then the derived category of coherent sheaves on Y has a kind of interesting piece, this Kuznetsov-Calabi-Yau category, and a bunch of exceptional objects. So let E be the sort of Fermat elliptic curve the sort of plane curve which has an interesting Z mod 3 action. Then E cross E obviously has a Z mod 3 times Z mod 3 action, and I can look at the kind of anti-diagonal action which rotates the two copies oppositely, so preserves the holomorphic 2 form on the product. So then that quotient, is a singular surface, but it inherits a holomorphic 2 form, so it's not hard to see that its resolution is again a K3 surface. So now you create 9 A2 singularities, so we resolved these with sort of 18 exceptional curves, and there are the 2 divisor classes coming from the elliptic curve. So this has Picard rank 20, and there are 9 sort of A2 resolutions. And the expectation is that there's again a mirror symmetry statement relating the Fukaya category of this K3 surface with Kähler forms living in an open cone in the sort of 20-dimensional space of possible Kähler forms you see, spanned by these 20 classes. So I guess I need a name for this resolution. But now the expectation is that this Fukaya category corresponds to the Kuznetsov K3 category of an appropriate mirror cubic fourfold, where again the particular monomials showing up in the defining equation of the cubic fourfold sort of encode information about the cohomology class of the Kähler form omega. So let me just say a word about where this comes from. Why should one think something like this? Well, this sort of elliptic curve E maps down under its Z mod 3 quotient to P1, and the P1 comes with sort of 3 orbifold branch points, and the complement of those 3 points contains Paul's sort of famous immersed circle. So E times E maps down to P1 times P1, and this contains a sort of affine open containing the sort of self product of this immersed circle with itself. So this singular K3 surface E times E mod Z3 contains sort of various immersed tori. They become embedded upstairs in E times E, which are lifts of this red curve. So, Nick didn't talk in the general Green-Plesser story about what the input to proving homological mirror symmetry in the very first step there was. That's to say, he said, take this category A. So in the Green-Plesser story, one uses the fact that these hypersurfaces in sort of toric varieties associated to simplices are ramified covers of projective space or weighted projective space, which again contain the Lagrangian kind of higher dimensional immersed sphere in the pair of pants that he's spent so much time sort of understanding thoroughly. That's the sort of Fleur theory input. So there's again a story here in which there's some well-known Fleur theory input downstairs, and then there's some story with coverings, compactifications, and resolution. The fact that these Lagrangians that we naturally encounter are immersed rather than embedded means that there's some more work to be done, sort of maybe lots more work to be done. So this isn't a theorem, but I think we understand many things about how we should proceed. So why is this potentially interesting? Is the
Y and where is the Kuznetsov category?
So the Kuznetsov category, so here, Y circle d omega is a cubic fourfold whose monomial equations depend on the cohomology class of omega via some mirror map, and I'm not taking the entire derived category of coherent sheaves for that cubic fourfold. I'm just taking its Kuznetsov category, which is a CY2 category associated to the cubic. And I'm saying that that CY2 category, which is a sort of admissible subcategory of its derived category of sheaves, that's on the B side of mirror symmetry, and we're trying to interpret that as the Fukaya category of a K3 surface. Is that clear? So as Daniel explained, for a generic or a general cubic fourfold, this Kuznetsov category is not the derived category of sheaves or twisted sheaves on an actual K3 surface. And indeed, here, if omega is again irrational, in the same sense that the sort of coefficients of these 18 exceptional resolution curves and the two classes coming from E times E are linearly independent over Q, then sort of the corresponding K3 category can't be geometric somehow for lattice theory reasons. So this comes from work of Addington and Thomas, maybe predates them, but that's where we learned it. One would find that this category has sort of no object which behaves like the skyscraper sheaf of a point. So there'd be no object with the right non-zero Chern character to look like the skyscraper sheaf of a point. And back on the symplectic side, the corresponding Z omega contains no Lagrangian torus of Maslov class 0, which is essential in homology. Maybe it contains none at all. I'm not quite sure, but at any rate, it couldn't contain a special Lagrangian torus, for instance. This looks to be, a setting in which usual ideas about mirror symmetry for K3 in terms of torus vibrations or family Floer theory might struggle. And finally, using some results that Daniel proved but didn't talk about yesterday, again in this generic case, so this irrational case for omega, the autoequivalences strictly of Fourier-Mukukai type of this category Y are known, and actually after dividing out by the square of the shift, which I've done implicitly every time I wrote down an autoequivalence group without telling you till now, the autoequivalences look like a Z mod 3, and it's the Z mod 3 we see very well in our story. We had E times E carrying a Z mod 3 times Z mod 3 action. We divided by one of them, the K3Z has a residual Z mod 3. So, for instance, one learns something about, sort of any symplectomorphism of this K3 with an irrational Kähler form acts Floer theoretically like, one of the obvious three maps you see. I'm over time and I was told I had to stop on time. Apologies. Thank you for listening.